So the four of you wrote a lot of papers together
We
at
did.
SOL. What were some of the other highlights?
Well, we wrote papers and we wrote software. So we all believed very much that we should prove theorems about what we did, and we should also write software. And so we wrote software together. And I mean, Michael, you are familiar with the fact that people have different styles in software. So writing a major piece of software was a big production, getting everybody to agree. And also, I think it's true that writing a program to do something is much harder than writing a paper about it. In the paper, you can say, there exists a positive constant such that this is true, and then you can prove something. When you're writing the program, you actually have to set the positive constant. You have to say what it is. Or you can say, the user can pick this positive constant, which they don't like. So all these details that you can sort of not pay attention to when you're writing a theoretical paper, you have to deal with when you're actually writing code. And you know, the other thing is, with floating point arithmetic, we're numerical analysts, so we think about finite precision. Lots of results that hold with exact arithmetic do not hold in finite precision. And you have to be aware of that when you're writing software.
So was NP-Sol the most influential piece of software that came out of that?
Probably. Nonlinear programming, SOL could sort of stand for Systems Optimization Lab or Solution. Right, exactly.
And then there was QP-Sol,
NP-Sol,
LU-Sol.
QP-Sol, LU-Sol.
And they were all interrelated, I
Right,
think.
right. LU-Sol was, I wasn't so involved in that. That was Michael Saunders. He's really the main linear algebra figure there, and that was his work. But even then, we all had something to contribute.
And did the other faculty at Stanford, Danzig in particular, and say Dick Cottle, did they take much interest in this software that you produced?
I don't think so. I think they were happy we were there. They were happy to have an enterprise that was working on software. George, in particular, had written a number of papers called something like On the Need for a Systems Optimization Laboratory. His idea was, and these went back to the 60s, I think, where he said we need a place where people can get together and talk about algorithms and implement them and actually solve big problems. He was very worried about huge problems that come up. He called them systems optimization, where you have big systems of complex parts that work together. And he wanted people to be able to solve those problems. That was his big interest in life, was solving those problems.
With integer variables? Was that a big thing for him too?
Not as much, but somewhat. I mean, George, we used to think, does George actually write software? See, I don't even know the answer to that. I tried to find that out. Did George Danzig himself sit down and write programs? And we think maybe he did, but he didn't talk about it much. But he knew exactly what they did. He knew how they worked. And, you know, he made so many wise comments about, have you taken care of this case? Have you done this? Have you done that?
Who were the users for the software, and were you heavily involved with them? Did they give you a lot of feedback?
People who work on the algorithmic side of mathematics. So I've been on many committees where we talk about what is mathematics? What's the end result of mathematics? And some people will say theorems. You know, we prove that this result is true. Others say it's algorithms for solving problems based on theorems. I mean, you don't just make them up, but you want a way to solve a problem. And very seldom is that done by writing symbols on a piece of paper. There are symbolic software systems, such as Mathematica and Maple, that allow you to do symbolic computations, but an enormous amount of interest exists in numerical solution of problems. So when you're a numerical analyst, a die-hard numerical analyst, which I am and many people are, you produce algorithms, and then first of all you want to say, all right, I have proved that this algorithm is good, it has a good rate of convergence, it's accurate, whatever. I think I'd better try it. I'd better run it with some real numbers. So you do that, and maybe it works the way you thought, or maybe it doesn't work the way you thought. And then you say, well, now I've proved that this thing has to be negative, but actually it's not negative. So there's either a bug in your program, or you've run into a problem with floating point arithmetic, or the problem's ill-conditioned. So lots of notions about the condition of a problem and when is the computed solution accurate, when is the computed solution close to the solution of a nearby problem, all these things in error analysis and so on, which were pioneered by Jim Wilkinson, to a large extent become important.
And these were points that you made quite emphatically in the book, is that
Exactly. So when we were at Stanford, our group, working on solving it, so let's say we thought of a method, NP-Sol, a sequential quadratic programming method for nonlinearly constrained optimization. So we have a theory, we prove it converges, we show that if you adjust things in a certain way, it will get to the solution. If you have the exact second derivatives, it'll converge quadratically. Well, that's fine. And you could stop there, and you could publish this. But of course, we weren't satisfied, so we said we'd better write some software to do this. So sometimes we'd start with a simple case for us. But if you write software, you rapidly discover that it's more complicated than you think initially, because you have to take care of all these cases. For example, let's suppose you have a problem where you have nonlinear constraints. And you say, let's assume a solution exists, a point exists satisfying these constraints. Then we can show such and such. Well, maybe someone will come along with constraints where there is no point that satisfies them. So do we just have it run forever till the person gives up, or do we say, well, we'd better have a test that if there's no feasible point, we'll do something sensible. What does sensible mean? And so on. So you gradually make it more and more complicated, and that's why when you have a conceptual algorithm, you can just sort of leave all those things out. Even deciding when an algorithm has converged correctly is a complicated problem. It depends on the scaling of the problem, the condition of the problem, the floating point arithmetic, and so on. And then once people hear that you have software, now we were working way in before the days of open source, they'd say, oh, I hear you have software that will solve this problem. Philip and Walter worked on a whole software library at the National Physical Lab before they came to Stanford as part of the numerical algorithms group library. So engineers, scientists, people that work want to solve their problems, and they don't want to write the software. They do not want to take the paper and write the code. So Philip and Walter had a long history of doing that. We continued that at Stanford. And then people hear about it, and this is even before the web or the internet, and they'll say, I hear you have a code that does this and that. Michael Saunders and Bruce Murtaugh wrote this famous code, Minos, which was for linearly constrained optimization. And they became extremely popular. But what happens, I'm smiling because it's so familiar, you put the software out and make it available. You don't necessarily make a profit, you just put it somewhere. And you put all these cautions, like only use this if there's a feasible point for the constraints, only use this if this is true and that's true. Well, people just ignore that. They just take the software, they run it, it doesn't solve their problem, and then they call you or send you an irate email. Your code doesn't work, it's garbage, what's wrong with you? And so you either get a very thick skin and ignore that, or you try to fix it. Maybe they've identified a problem. So you keep working on it, and that's why some people say writing software is never convergent, because you're always trying to make it better, and you're always trying to solve problems that came up. That's one of the reasons people have gone to open source, so that you find a bug in someone else's program, you can fix it.
And who were the users?
I would say other people in optimization who may have had the motive that they had a new method that they wanted to be better than the method we had, so they wanted to run our code so that they could show that theirs is better. People in science and engineering who have optimization problems to solve constantly. And people in other applications like business. Linear programming is very important in business. But sometimes in business, the problems are not linear. So they would say, it would be wonderful if we had a code that could solve nonlinear problems with linear constraints or whatever. So there's a huge market for this. And it's also sometimes valuable for teaching. Someone who's trying to teach about this kind of method can have the students run the program and see what happens.
Were there ever cases where the users would feed back to you and then you would end up working with them and perhaps end up collaborating?
We did that a few times. I mean, sometimes people would say, we want to solve this optimization problem and we don't know how, and are you willing to be a consultant about this problem? And sometimes we were able to do that. Sometimes they would say, we'll pay some money to Stanford if we can get a license to use this code in our products. So let's say a big company wants to have some kind of chemical simulation and they want an optimization routine. And they want to put your routine in their thing. Well, the university has the view that, okay, we should get something back for that. So there are different kinds of relationships.